Hello, welcome to this Vib Tip session. Today we are going to talk about hardware to see and record how our device under test is shaking during the vibration. Seeing the movement of our device under test during a test will definitively help us to understand the vibration modes, detect the stress parts, and take the decision on where to locate the accelerometers for a consistent control strategy. We'll talk about three types of equipment: stroboscopes, stroboscopic cameras, and high-speed video. Stroboscope generates a strong flashlight at a controlled rate programmed either in cycles per minute or in hertz. If the illumination of the lab is low, our eyes will only see the scene when the flash is activated. Initially, let's imagine we generate a flashlight at the same frequency as the vibration sine excitation. In that case, for each period of the sine wave, we'll see one position of the DUT, and for our eyes, the DUT seems to be stopped. Shifting the phase of the flashes, we could see the DUT stop at different positions. Now, let's generate a flashlight at a slightly lower frequency than the vibration sine excitation, normally 1 to 3 Hz difference. It means that we will illuminate the DUT a bit later each cycle, and then, in front of our eyes, the DUT will be moving at the frequency corresponding to the difference between the excitation and the flashing. This feature of a stroboscope is called slow motion. Up to now, we were considering sine excitation at a constant frequency, but the flashing light can work as a slave of the excitation frequency in order to maintain the effect even during a sine sweep. In this configuration, the flash's rate will be changing accordingly to the instant excitation frequency of the sine test, and we will see the DUT shaking at 1 to 3 Hz all through the testing frequency band. The synchronization can be done using a constant voltage output proportional to the excitation frequency called COLA output, or through a tachometer output from the vibration control. Below, an example of the resonance of a beam recording using stroboscopic illumination. Similar concepts are behind stroboscopic cameras. In this case, instead of using the light of the strobe to freeze the movement of the DUT vibration movement, we keep a constant illumination, and we use a very short exposure time of a digital camera. Through a dedicated hardware, the shutter opening is synchronized with the COLA output, looking for a zero crossing every several cycles. That depends on the maximum images per second of the digital camera, and adding each time a phase shift that continuously increases. Therefore, as we see in the image, the movement of the DUT is slowed down. It's important to take into account that these systems are useful for sine vibration testing due to the periodic nature of the vibration and the possibility of synchronization with the excitation frequency. In random tests, since we are exciting at many frequencies at the same time, these devices don't give a good information. We can use a high-speed video and a strong illumination lamp to directly record a sine excitation. Experts say that for human eyes to recognize a sine wave, it's necessary to get at least 8 to 10 images of the period. Therefore, the frames per second rate of the video should be 8 to 10 times higher than the excitation frequency. This limits the typical 500 frames per second models to less than 60 Hz, and the 2000 frames per second models range to no more than 250 Hz, too low figures for many applications. Additionally, there is also a strong restriction in the duration of the sine wave due to the internal memory capacity. Nevertheless, high-speed videos are widely used for image recording of non-periodic signals as transients or random tests, where the high frames per second feature can let us see short-time events. However, if our high-speed video frames per second rate can be externally controlled, we could use the imaging recording event as we were previously used in the stroboscope, so slightly shifting the frames per second rate versus the sine excitation frequency. Doing so, we could even record sine tests up to 2000 Hz with, for instance, a 2060 frames per second high-speed video. Here, I have put some examples of slow motion images, both sine and random tests, to illustrate the possibilities and the quality we can get recording with high-speed video. Summarizing, viewing the evolution of a sine test can help test technicians to understand modal shape of our DUT and define the best location for control accelerometers. It can also be highly clarifying for customers, management, and other departments in the company. Well, thanks again for attending, and let's meet in the next Vib Tip session.